Have you ever picked up a really soft, kind of silky shirt and just wondered, where did this actually come from? You might guess cotton, maybe silk, but what if I told you it could have started its life as a tree? Yeah, you heard that right. Today, we're going to get into the absolutely incredible science that turns solid wood pulp into the amazing fabrics that we all wear every day.
It really does sound impossible, doesn't it? I mean, how in the world do you go from a rough, solid tree to a soft, flowy t-shirt? Well, it's not magic, it's chemistry. And that's the exact puzzle we are going to solve together. We're going to break down this whole fascinating process, from the forest all the way to the factory. So, let's get into it.
All right, here's the game plan. We'll kick things off with the basic three-step recipe that's behind almost all of these fabrics. Then we'll take a look at the original game changer, viscose rayon. After that, we'll check out some of the modern upgrades, like lyocell and acetate. And finally, we'll connect all that lab stuff back to the actual clothes hanging in your closet.
Okay, first things first, the fundamental formula. You see, before you can make any of these special fabrics, you need a universal starting point. The biggest hurdle to overcome is figuring out how to take something solid, like wood pulp, and turn it into a liquid that you can actually spin into a tiny little thread.
Now, this is the key concept right here, regenerated cellulose. We are not making some new synthetic plastic from oil or something. Nope, we're starting with cellulose. That's the natural stuff, the polymer that makes up the cell walls in plants. The whole process is about dissolving it, processing it, and then putting it back together, or regenerating it, in a totally new shape. So think of it less like inventing something new and more like rearranging nature. And that regeneration pretty much always happens in three main steps. First, you dissolve the pulp using a solvent to get this thick, gooey liquid. Second, you extrude it. Seriously, just picture a high-tech pasta maker or even your shower head. This liquid gets forced through a thing called a spinneret that's full of tiny holes. And then third, as those little liquid streams come out, you solidify them almost instantly, turning them back into solid little threads. Dissolve, extrude, solidify. That's the blueprint for everything we're about to see. So, with that blueprint in mind, let's see how it was first used with the original man-made cellulose fiber, viscose rayon. This was the OG, the pioneer technology that first proved you could make these beautiful, silk-like fabrics from, well, trees. It was a huge deal. Okay, so the process begins with these big, purified sheets of wood pulp. The first thing they do is soak them in a bath of caustic soda, which starts a chemical reaction with the cellulose. Then, they're pressed to squeeze out all the extra liquid and are fed into a shredder. This thing basically just chews them up, turning these dense sheets into a light, white, fluffy material that honestly looks a little like cotton balls. This stuff is called alkali cellulose. And here comes the real chemical magic. That fluffy alkali cellulose gets tossed into a giant rotating mixer. Then they add a chemical called carbon disulfide. As it all churns together, the white fluff starts to change, first turning yellow and then a deep orange. This creates a new substance that then gets dissolved in a weak caustic soda solution. And what you're left with is this thick, sticky, honey-colored liquid. And because it's so, well, viscous, that's exactly where the name for the whole process comes from, viscose.
All right, time to spin. That thick viscose liquid gets pumped through the spinneret, pushing it out into a chemical bath. This bath is filled with, among other things, sulfuric acid. And the second those streams of viscose hit the acid, the chemical reaction reverses itself. The dissolved cellulose instantly solidifies. It regenerates into solid filaments of rayon. From there, the threads are just gathered up, washed, and they're ready to be spun into yarn.
Now, the viscose process was absolutely revolutionary, but you can tell it's a pretty intense chemical process. So let's move on to the innovators. Scientists have spent decades tweaking and totally reinventing this process to create brand new fibers with different properties, and often with a much smaller environmental footprint.
And the real star of that eco-friendly innovation has to be lyocell. You probably know it by its most famous brand name, Tencel. Lyocell isn't just a small step forward. It's a massive leap, especially when it comes to sustainability.
Just look at the difference here. On one side, you've got the classic viscose process, which is this complex, multi-stage thing using some pretty harsh chemicals. But then you've got the lyocell process. It uses a non-toxic organic solvent to dissolve the wood pulp directly, which is way simpler. But here's the real game changer. It's what's called a closed-loop system. Over 99% of that solvent is captured, cleaned up, and used all over again. That just massively cuts down on waste and environmental impact. It's really clever. But what if you don't just want to rearrange the cellulose?
What if you want to fundamentally change it? Well, that brings us to a whole other category, modified cellulose fibers. In this case, the cellulose molecule itself gets chemically changed to create a brand new substance with totally different behaviors. And the classic example here is cellulose acetate.
So to make acetate, you react cellulose with acetic acid, which, fun fact, is the same acid that gives vinegar its sour kick. This reaction swaps out parts of the cellulose molecule and sticks on these acetate groups, creating a whole new polymer. And this is where the chemistry gets really cool, because this new polymer is thermoplastic. What does that mean? It means unlike rayon or lyocell, it melts when you heat it up.
And that ability to melt allows for a completely different way of making it. Remember how viscose and lyocell had to be solidified in that liquid chemical bath? That's called wet spinning. But with acetate, the polymer gets dissolved in acetone, a solvent that evaporates really, really fast. So they just extrude it through the spinneret into a chamber of warm air, and poof, the acetone evaporates away, leaving a solid fiber behind. This is called dry spinning, and it's a much faster and simpler process.
Okay, so we've been through a lot of chemistry, a lot of different processes. But why does any of this matter, right? In this last section, we're going to connect all this lab work to the real-world performance of the clothes they make. Why would you actually choose one over the other?
Let's have a little fiber face-off here and focus on what happens when these fabrics get wet. Take a look at that first row, wet tenacity. That's just a fancy word for strength. You'll see standard viscose rayon can lose about half its strength when it's wet, which is why you have to be so gentle when you wash it. But look at lyocell. Its tenacity is more than double. It holds up incredibly well. This is because the lyocell process creates a much more uniform fiber structure. You can even see it in that last row. The cross-section of a viscose fiber is all jagged and serrated, while lyocell is smooth and round. That smoothness makes it way more durable for day-to-day life.
And the result of all this incredible science is a huge range of products that we use literally every single day. From the lining inside a nice suit jacket to super soft bed sheets, and even in really high-tech stuff like tire cord and medical supplies. These fibers, which all started out as wood, are absolutely everywhere.
So we did it. We went all the way from a tree to a t-shirt, from a simple plant polymer to high-tech textiles. It just goes to show you how chemistry can unlock all this amazing potential hidden inside natural materials. And that kind of leaves us with one final thought to chew on. If trees are our renewable starting block, and our processes are getting smarter and more sustainable all the time, what might the next generation of fabrics look like? What other incredible properties are just waiting for us to unlock from the forest?